All right. Welcome, and thanks for coming to Swift Language User Group. Thanks for the talk, Brett. I'm very excited today to talk about something that I've been digging into a little bit on the Swift side for the last month or two, and that is a very hipster subject. I hope you wrote in on your fixies, you have your horn rim glasses, you're sipping your espressos or macchiatos, and we'll talk about bespoke artisanal Swift static analysis. And throughout the talk, hopefully it'll make a little bit more sense as to why I chose to kind of look at it from that angle. So recently, I mentioned I was digging into this. I saw this tweet from John Rieger, who is this compiler expert, well known in the community. And he shared that there's, as far as he knows, only one good resource for what is static analysis. And so he links to this paper. And so it's called Static Program Analysis, right? Looks approachable enough in that wonderful serif font. And it's updated fairly frequently, right? So the latest update was just about 2 weeks ago. And so, okay, you start digging into it. And it starts with this really easy to grok explanation. What is static program analysis? Well, it's effectively the art of reasoning about what the behavior of computer programs are without actually running them, right? So you look at source code, you look at a collection of computer program files, and you try to infer what some of the behavior from it is, okay? All right, that seems straightforward enough. How hard can this be? It's really just trying to get information from source. Okay, so you start reading the paper, and it shares some fairly simple concepts like intraprocedural control flow graphs, lattice theory, monotonicity, constant propagation analysis, very busy expressions, transfer functions, closure analysis of the lambda calculus. And then as you read this thing, you start to realize that there is no way in hell that you can comprehend this without a PhD in computer science, and even then in static analysis. So I have as much chance of building a static analyzer as this guy does washing his car. Like, sure, you'll get it wet, but you'll probably get soaked in the process and bloodied and bruised. So you start over, and you start with the basics, and you hope that Google will help you. And Google does not help you. So again, you go back to the drawing board, and you ask yourself, well, how hard can this be? Again, Objective-C has a static analyzer. Objective-C, for those of you who have never heard of it, it's this really old language from a long time ago. Actually, Objective-C is like almost 30 years old. It's fascinating to consider. And so some of you have probably heard or used the Clang static analyzer, this Command-Shift-B command that you can do from Xcode for those of you who were building apps since before 2014. And it was an extremely useful tool, still is an extremely useful tool. So Clang stands for C language. It's this front-end compiler for the C family of languages. It sits on top of LLVM that can compile C, C++, Objective-C, and flavors in between. And so the Clang static analyzer is this open source static analysis tool. It's built on top of Clang and LLVM. All right. So very useful. You can infer behaviors about your source code, such as objects that are missing, or retain, or release, or all sorts of things. So, okay, how does this transfer over if we were to do something like this for Swift, right? Well, if you were to do this correctly in a correct way, you probably want to build this in a similar way as the Clang static analyzer is built on top of Clang and LLVM, right? Swift's also built on LLVM. And so you could probably build it on top or maybe alongside that, because you need hooks into these more Swift and LLVM specific things. So you probably wouldn't really be able to build it on top of Swift, because Swift doesn't really have all of these hooks that you can hook into. So maybe you'd need to build it as kind of a side thing as part of Swift and LLVM. but you'd really need deep understanding of how the Swift compiler works, how the LLVM subcomponent works as well, which is a massive undertaking. All of this is written in C++, and so you'd need some familiarity with C++ to do this right. And not only that, but you'd need to be really familiar with real static analysis concepts. Again, I mentioned control flow graphs earlier. That's effectively a way to model the control flow, so the path that your code takes as part of source code. So all of this is fairly complex stuff. So, if you're me, you start to think like, is this really what it's going to take to build a little tool that I can just get a little bit more information about my source code from? And, I was asking myself, is there a world in which it's possible to build something that, won't take a full-time job, several months to do, right? It'll be simple to extend and simple to build, fast to build, right? I wouldn't necessarily want to require so much deep knowledge of this complex machinery that is the Swift compiler in order to get something done here. And can it be easy to run, right? Like, do I need to build a full custom tool chain of the Swift compiler with all of my hooks in there and constantly rebase that and patch that every time there are updates to the language? And is there a way for me to build this in a way that you don't need to be a C++ or a compiler internals expert? And this is where this bespoke artisanal Swift static analysis comes in, where maybe we can build something that's one-off, something that we can handcraft and not require a team of software engineers to develop. And so you distill it back to its basics, and you need a few things, right? And you don't need to be a static analysis expert to come up with these, right? You need a way to run over source files that you want to analyze. Easy enough. You need to perform an action on that source. And then you need to get detailed information about that source. This is where it gets really tricky. So once you get all of this detailed information, well, then you need to convert that to something that is actually interesting, right? You can infer so many things about source code, but if you can't translate that into potential bugs or actionable things, then it's not very useful. You need a way to report these interesting results to the user of this tool. And then you need to, ideally, a way to act on these results, right? Like a next step, a suggested correction to whatever problem you find via static analysis. Well, this is where SwiftLint comes in. And I really don't mean this talk to be a pitch for SwiftLint. I really just kind of want to show a potential path forward. And I really hope, actually, that people kind of look at the concepts from here and kind of do their own thing. But SwiftLint's this tool that can typically look at source code and mostly from a syntax point of view, try and identify things that you might want to change about it. So a lot of this is used for style, for code style, but even today it has a number of things that go a little bit beyond that by kind of just looking at the shape of code, maybe identifying some suboptimal code patterns and things like that. But even then, it's pretty limited because it only uses the pre-type checked abstract syntax tree. So it only uses the steps after the lexer and the parser, or the parser and the lexer. So effectively, all you can really say with SwiftLint today is, okay, well, this is a keyword, this is an identifier, this is a type, this is a new line, this is a comment, things like that. And then you can get effectively the structure, right? Like this is nested within that, within this, within that. Which gets you pretty far, but this isn't the kind of detailed information that we want. But still provides a useful base to then build our bespoke artisanal static analysis tool on top of. Because we can check off a number of the kind of more boilerplate things that we need to build a tool like this. We can run over the source files. We can perform an action on all this source. We have a way to report results. We still don't know this kind of middle bit, right? We have question mark, question mark, question mark, profit. But we have a way to report the results and then to act on these results because SwiftLint already does that. So all that's left to do is to figure out a way to get this detailed information and then to convert that and extract interesting results out of it. And this is where it really does take some experimentation and some thinking outside the box a little bit. So yeah, easy. Let's try and figure out how to do this. Well, it turns out that Swift already exposes a mechanism, the Swift compiler exposes a mechanism to hook into it, albeit very indirectly, via this, this tool that's open source. It's part of the Swift code base. It's called SourceKit. And you've probably seen this, especially if you've been coding with Swift for a few years, because SourceKit has usually been the gateway to people seeing how unstable the Swift compiler has been, especially early on. It's a lot more robust today. And so it's this tool. It ships with Xcode. It ships with Swift toolchains on macOS, on Linux. So it's available, and it provides a way to hook into some of the compiler functionality without necessarily interfacing directly with the compiler. So if you've ever worked with Clang, you might be familiar with libclang, which is kind of the analog to SourceKit for C languages, and it's a way to go and parse source files and extract more information out of it. So there's some interesting requests that you can send this SourceKit tool. You can send an editor open request, which is the exact same request that Xcode sends as soon as you open the file. And this is the request that would give you syntax information. This is the request that SwiftLint operates on today. So you have the pre-type checked AST. And what's great about this is that you can just pass it in any plain old Swift file, and it will parse it and give you actionable results out of it right away. However, Swift is more than just a single file at a time, right? When you're writing a Swift app, you're actually hopefully using a collection of files. Hopefully you don't have your whole Swift app in a single app delegate.swift file, although you can. And so this editor open isn't terribly useful if you want to infer things like, how does this Swift source coexist with the greater whole, with all of the other Swift files in that module, with that module's dependencies, et cetera. And this is where you have two additional source commands that are super useful. You have the index command and the cursor info command. And these require compiler arguments, and these are a little bit harder to use, especially compared to kind of how a tool like SwiftLint works today, where you just pass in a big bag of .swift files and it can start acting on it right away. If you then need to pass in compiler arguments on top of that, that gets a little tricky. Xcode does not like giving you its compiler arguments. It does not have an easy way for you to introspect that. And so you need to come up with some creative ways to resolve that. Anyway, let's dive a little deeper into what these requests do and how we can use them. Remember, we're still at the stage of trying to get detailed information out of our source. We don't even know how to convert this to useful information yet, just detailed information. So for example, you look at this very simple Swift file. You have a struct A with a function inside it, a member function called B. So it's kind of hard to read here, but really I just kind of want to show the high-level aspects here. If you perform this command, you can get a few interesting tidbits out of this Swift source so far. You can tell that there's a struct, and that struct is called A, and you can tell that there's a function that's an instance method that's called B. And then you can tell a number of other information, such as kind of this nesting structure and some properties about where these things exist, their location in the source file, and things like that. If we look at the same file and we perform the index command, again, this needs compiler arguments for this to work correctly. So you need to pass in all the compiler arguments that this one particular file would need to coexist in kind of the greater whole of your entire Swift module. Then you can also get some different interesting information out of this. Again, you can tell that you have a function named B that's an instance method that lives in a struct called A, but you have one more thing. And you have this USR, which is a unique symbol resolution identifier. It's basically a unique ID for all Swift declarations. And this is terribly useful because Swift is not a simple language. You can have the same method name peppered 100 different places in a code base. Imagine a method called reload or or fetch or some generic term like that. And this kind of brings us to why we need richer information out of source, because you can't just rely on string parsing to do things like more semantic static analysis. And we'll get to that in a minute. So we're getting one more useful piece of information here, which is that USR. And this will come in handy because it's a way to tag every single declaration of code that we find in our code base with a unique ID. And then we'll be able to cross-reference that later. Finally, we have the cursor info call, which is, as you might infer, the exact same request that Xcode does when you option click on a symbol. And typically, you can do that to see that symbol's documentation, but under the hood, what this is doing is sending a request to source kit for a number of interesting aspects for what's under that cursor. So let's skip over, and some of the contents that we might find are its accessibility level. For example, is this internal, private, file private, and this is less trivial than you might think because you have a number of implicit access control levels in Swift. Think of if you were extending an internal type in your code base in a different file, and then you add a method. Well, without knowledge of kind of what access control level that file has, or that type has, there's really no way, just by looking at that single piece of Swift source, to know what that access control level is. Same thing with enums or nested types or things like that. So this is where relying on the Swift compiler to tell you this is a lot more reliable than some mishmash of kind of home-rolled parser that you're trying to build yourself, right? So this is why you rely on the official tooling. You have annotated declarations. So this is a source kit response that includes kind of the XML annotated source for what you're inspecting. And right now, this is a very simple function, but if you had parameters or if you had return types, they could infer that for you. So this is useful as well. File path, annotated declaration. Method instance, we already have this. There's a number of things that we have still already here from previous requests, but then the type name also becomes very useful, where if you want to know exactly what the type of a method is or a declaration, sometimes just parsing the source, the string itself is not enough. You kind of need to know what is this referencing and what are the definitions for that. So there's a number of much more useful information that we do that we can access with this request. Okay, so now we have a number of different ways that we can get more detailed information out of our source. How do we create anything useful or anything interesting out of that? And this is where I want to share a few examples. So these are actually, there's a number of rules that are already open source and built into SwiftLint now, added just a few weeks ago, and they give you an idea of what kind of tools you can build on top of these underlying fundamentals. And one of them is finding dead code. So for example, say you have these two structs. You have fika, which is effectively like a Swedish pastry, and then on it you can call an eat function. You have a bagel, which you can also eat. And in this source code, say this is, obviously we're drastically simplifying here, but say you have an app with 100,000 lines of Swift code, right? Well, even if these are defined and used in different parts of your code base in different source files, you can still perform this whole analysis on that. So in this case, our whole program here is only invoking the eat function on the fika type. And then at the very bottom, we're printing an instance of bagel just so that we're using it. So in this case, we have dead code. And it'd be useful to find dead code, especially if you have a large, complex app with lots of people working on it that's constantly being worked on, because dead code is obviously bad for a number of reasons. It adds more time to compilation. It can sometimes actually highlight that there's a bug where you were trying to call something, but you inadvertently called something else. And so finding unused code is a very useful thing to do, and that's where we can turn to static analysis. So I don't want you to necessarily read this verbatim, but effectively, to build a static analysis rule on top of this detailed information that we just talked about, there's 3 steps. Okay, so you're trying to find unused code. So what is unused code? Well, you take all of the different declarations of code that you have in your code base, right? So you declare a struct, you declare a function, et cetera. And then we saw earlier with the index call, we can find out what the unique symbol resolution identifiers, what those unique IDs are for all those declarations. So you just make a big list of all these IDs of things that are declared in your code base. From that, next, you look at everything that is referenced in your code base, right? And this is where the cursor info call comes in. Every time you make a cursor info request, you can see if it's a declaration or a reference to something that's being declared elsewhere. So say you're, in our previous example here, the second to last line where we're invoking the eat function, that's a reference. We're referencing the eat declaration that's declared on line 2. So again, you make a big list of everything that's declared, you make a big list of everything that's referenced, and you subtract one from the other. And everything that isn't directly referenced that was declared is dead code. So in this case, we can perform a filter on all of our USRs and say, well, if any of these are not referenced, it's dead code. So in this case, we found that the bagel.eat function was unused. Obviously, it's a very simple example, but sometimes you can find huge swaths of your code base, especially if you have a large project, that was migrated away from, and someone just forgot to delete the initial source. And this can be extremely useful to find. One thing that I found out by building this is that I realized that there's actually a large amount of Swift code that is indirectly used, not directly referenced. So, for example, not that I advocate for this exact use case here, but it's a good example. If you have a weekday enum, we have Monday, Tuesday, Wednesday, Thursday, Friday, and then you have an extension on string that checks to see if it's one of those weekdays. Well, in this case, we never directly reference any of our enum members, but we require them to be present for this code to work, right? If you remove Friday from your weekday enum, even though because it's dead code, your code all of a sudden changes. So you have to keep that in mind. And not only that, there's a few more cases where code can be indirectly used. One other example is dynamic code, right? So if you have any code that's only ever used via interface builder, IB outlets, IB actions, at obj_c methods. Sometimes these are only accessed dynamically, so you have to watch out for that. And then finally, protocol conformance code. This one's a little harder to see, but if you have a protocol called food, and you have an eat function on that, and then fika and bagel both conform to that protocol, and then you never directly eat a concrete instance of either type, you only ever eat the food protocol or something that conforms to it, then those individual conformances might be unused because they're not directly referenced. So those are all a few cases that you have to watch out for. So yeah, just kind of sharing some findings that I found interesting while building this. And then along the same lines, you can build a way to detect unused imports. So in a similar way as dead code, unused imports can be indicative of a larger systemic issue with a code base. For example, you might think that you rely on a number of frameworks for a certain part of your, like maybe you've split up your app into multiple frameworks, and so you have this dependency graph. And you might think it might be overly complex because you think that some modules depend on others when in fact they don't. So detecting unused imports can be a good way to identify that. Really simplify your dependency graph, simplify your entire application architecture, really. So in this case, we've defined a dispatch main function on an A struct, and then we invoke it. So there's this dispatch main free function in the dispatch module, in the Grand Central Dispatch module. But in this case, we're not accessing it. And if you're relying strictly on kind of string-based, non-semantic code detection tools, you wouldn't really notice that you're not actually using anything from that module. And of course, this can be any module. It can be a module that you've defined yourself. It can be a system module. It can be a number of things. This is actually super useful if you have a code base that you're trying to, say you have a module that you're trying to extract and make portable so it can run on Linux and on Darwin platforms, but you're depending on UIKit in a bunch of places. Well, what we found in Lyft's code base is that where we were previously importing UIKit, we're only using things that were defined in Foundation, or sometimes nothing at all. So sometimes you're only using the transitive import. So these are actually really useful to find and can really help clean up your code base. So in this case, how would you build a static analysis rule that can find your unused imports? First, you find all of your imported modules, right? So in this case, a cursor info request on the dispatch import would show you that it's a reference to the dispatch module, right? So you kind of make that request, you store it somewhere. And then you go through the rest of the source, and you see you perform more cursor info requests. And if ever there are references to declarations in other modules, the cursor info request will return what module name that's referencing. And so you kind of make a big list of all referenced modules. And again, you do the same thing that you did for unused code, dead code, where you subtract one from the other, and you find all of your unused imports. So those are two examples of some kind of static analysis type rules that you can build on top of the information that we found. A few traps here as well. SourceKit doesn't let you perform a cursor info request on operators. So sometimes if you're importing a module only for its operators or operator overloads, this won't find it. And then if you're performing an import, but you're only using the transitive dependency, that import might actually be used, but indirectly. So it's still indicative of a problem. You should probably constrain that import to just what you need, but it doesn't just mean that you can delete all of those lines, because sometimes your code won't compile after that. So just a little demo. If you were to use this today, you can, using Swiftlint from master, you can add these analyzer rules to your Swiftlint configuration file. We have 3 rules that are built today, but there's a lot more that can be built. And this is kind of where I'm hoping that the community starts pitching in on these. And then you run Swiftlint analyze. And then this is where the compiler arguments comes in. You need to pass in the compiler log path. So basically, if you run Xcode build on your project and you output that, you dump that to a text file. You need to pass that to Swiftlint analyze, because that's really the only way that Xcode lets you grab the compiler arguments that you need for all these SourceKit requests to work. So if you wanted to do this today, you could run these rules. You can work on your own rules, kind of run it in the same way. And this kind of meets our goals from what we wanted originally, right? Are these fast and simple to extend, right? Where you saw these unused examples are really just a handful of lines of code, right? Each of these analyzer rules can be less than 100 lines of Swift code, right? And you don't need to build the Swift compiler in order to have access to this. So as a little demo for Lyft, we ran this tooling recently, and for example, trying to clean up imports and dependencies that weren't actually being used in our code base of about 4,000 Swift files, we were able to delete. If you look at this PR here, it's pure deletions, no additions. We were able to delete 1,400 imports from our code base. And not only that, we were able to remove 70 dependencies as part of this process from some of our internal modules, because it turned out that even though we had imports for dependencies, those weren't actually being used. So this drastically simplified the build graph for our project. And of course, everyone loves deleting code. If you run this on your own code base, I'm sure you and your teammates will do a little dance, because deleting code is so much more fun than writing it. So I mentioned there's a ton that can be built on top of these primitives and on top of this information. So for example, you could find inefficient code patterns in your app, which can be indicative of bugs or simply just opportunities for optimization. So for example, if you're filtering a collection and then calling first on it, well, you might want to use first where so that you don't have to iterate through the entire collection the minute you find something. You could use these concepts to identify code that looks like it could be converted to a map or a flat map or a reduce, and use these more functional concepts, whether just for code style or, again, for optimizations. And this is where the bespoke and artisanal aspect of analysis comes in. Because these rules are fairly simple to write, you could even build something that's tailor-made exactly for your project or your coding style. So say you have an internal framework at your company that you prefer using over direct Apple APIs for some things. Well, then you could detect that using the static analysis and enforce certain code architecture style policies. One thing that we do at Lyft is we require explicit references to self for member accesses. It's strictly a code style factor, but this is, again, something where you need a little bit more than just parsing the Swift syntax in order to identify it, because sometimes you're in an extension in a different file, so you kind of need to map these together. So there's a lot that you can do. I really hope that the community builds on this, and I know I'll continue adding more rules here. So I want to leave you with a few thoughts. You don't need to read a 70-page paper on the basics of static analysis in order to come up with some useful tools. And really, this goes beyond static analysis, right? Just tools in general. I think we, as the Swift community, need to wean off of Apple a little bit when it comes to tools, and kind of understand that we have the power to build these kinds of tools ourselves. A realization, a eureka moment that one of my colleagues had recently was that, hey, tools are just apps. And it may seem obvious on the face of it, but it's true. And once you kind of realize that, it may make you a little bit more open to experimenting with building tools. Xcode may be closed source, but a lot of the building blocks that you'd need to build custom tooling is open source. Right? The number of times I see tweets of folks saying, curse you, Xcode, you're closed source and you're broken and there's no way to fix you. Well, most of the time, the broken piece is actually open source. So again, I encourage you to take a look at that. And then again, just kind of rehashing other language communities. You look at Rust, JavaScript, even some of those languages that are primarily driven by a main stakeholder company. It's not that company that provides all of the tools for everyone to use, right? And so we just really kind of need to embrace that. And I'm not, there are a lot of people who are already doing this, but I think there are even more people who are interested in doing it but don't know where to start, so hopefully this is a good jumping off point. Thank you. We can take 3 questions, and then we can chat some more afterwards and socialize.
So in your dead code example, if you said that the lexing and syntaxing tree stuff comes before the typing, how could you possibly know whether which eat function had been called if you haven't typed the receiver?
Yeah, totally. That's a great question. I probably just didn't make that clear enough, but with the editor open command that does not take compiler arguments, because it doesn't take compiler arguments, it returns to you the pre-type checked AST. What we're operating on here is the post type checked AST, which you can get once you pass in those compiler arguments, and then you can pass those compiler arguments to that index command and that cursor info command. So the results of those have context from the post type checked AST. Yeah, so yeah, great question.
I actually have two questions. So the first one is, what's the performance of running the tool like? And the second question is, have you compared your tool with another app called the Periphery app that's also, I think, kind of popular these days?
Right.
Yeah.
The performance is terrible. It is really bad. Yeah. So, for example, to run these analyzer rules on Lyft's code base of 4,000 Swift files, it takes about 20 minutes on my laptop. So it is bad. There's a number of things that can be done to optimize that. For example, most of the ways to optimize that would actually be to expose some batch functionality in SourceKit itself. And that is certainly possible. What I found is that even with this limited set of analyzer rules and the value that it provides, if it's something that you run manually every few weeks, I personally would rather do that and then sift through some of the false positive manually. Obviously, it's not ideal, and have it take 20 minutes versus not having a tool like this at all. So that's the answer to the first question, performance. The second question, how does this compare to Periphery? I don't know. I have not run Periphery. My understanding is that it applies a similar approach by tapping into SourceKit and effectively doing some similar things. But if anyone's more familiar with its inner workings, I would love to hear from you. Yeah, and honestly, like I mentioned, this was not meant to be a pitch for SwiftLint, only really just kind of to show that this kind of stuff is possible and kind of some of the basic fundamentals of how you could do this. And if someone wants to build something that's way better, either separately or make improvements to SwiftLint itself, I'm super open to it.
Can you speak to any changes in performance after you removed excessive imports? Did that have a significant impact?
Yeah, that's also a great question, and I have no idea. You would think that it'd be faster. Yeah, and no matter what, it feels good. So I don't know. I haven't benchmarked compiling before and after, but you're not the first person to ask me that, so I should really just do it.
All right, thanks, JP.